Okay, so welcome back. So the seminar today will be by Juan Valiente Kroon on asymptotics in general relativity, the role of spatial infinity. Well, Juan has done major important contributions to understanding how one can connect from spatial infinity to null infinity and the type of singularities that might develop. And I think that this will be the subject of today's seminar. So please.
Well, thank you very much, Mark, for the invitation. So it's a pleasure to be here. And yes, as Mark was saying, so I want to talk about my favorite topic, which is the role of spatial infinity in determining the behavior or the asymptotic behavior of the gravitational field. Okay, so there are several topics, so which are somehow the overview. So this is a very full slide, but there are 4 topics that I want to discuss today that they are interconnected, but sometimes they are studied or regarded independently from each other, right? So I want to stress here how all these 4 pieces somehow combine with each other, right? So one of the first things is that I want to stress how the asymptotic behavior of the gravitational field at null infinity, so where we observe radiation, is closely tied to the behavior of spatial infinity. And then this has a name in the literature, so it's called this problem of spatial infinity, or at least the part of literature I work on, so it's called this way. But then this is also closely tied to something you certainly have heard before, which is this idea of Penrose compactification. So it's a framework devised by Roger Penrose to study the asymptotics of isolated systems in general relativity. Right? And then I want to somehow indicate that these conditions, that at least in the original formulation, are very restrictive, and they will not really describe generic spacetimes. But then, so people have worked on how to deal with this restriction and how to understand whether this construction is generic. And then for this, I want to introduce or present a certain structure of spatial infinity. This is originally due to Helmut Friedrich, which is called the cylinder of spatial infinity, and I claim that using this representation, one can actually gain a full understanding between how Cauchy data for the Einstein field equations and the asymptotic behavior of the gravitational field are related to each other in a precise way. And well, just to make this come down to earth, so I also to discuss some application of these ideas to the computation of asymptotic charges, right? Which is a topic which has gained some relevance in recent years. Okay, so then I will start, as I said, so the talk is planned to be very conceptual, so it's high level. So there are a lot of details hidden in the statements I will giving. So if you are interested, then please ask or have a chat after for the talk. Okay, so right. So what to know is the idea of study of the asymptotic field. So the asymptotic behavior of the gravitational field is a topic with a long tradition, so probably going back to the early 60s. So there is really a vast literature, on this topic, which builds mostly on this Penrose idea of isolated systems using the notion of asymptotic simplicity. I will discuss this a bit more in detail. And I guess at least the old literature had a caveat, which is that most of it is really formal. So to make all these constructions work, one is a number of assumptions, which may or may not be generic, right? So it's just to stress that it's nice to have a nice formalism that allows you to determine whether you have charges or not, but in the space-time, the class spacetimes for which these assumptions hold is not generic, then it's probably not so useful, okay? So this is somehow the idea that I want to develop in this talk. Okay, so as I said, so in a topic which is spanning over almost 60 years, right? So there is a lot of work to try to set all the assumptions on a solid footing, and then I put some list of people who have worked here. So they are mostly the people I interact with. So this is definitely not meant to be comprehensive. And then, of course, so the interests and the approaches here are very different. So then I should mention particular Helmut Friedrich, which I think I'm going to cite his work quite a lot. And I've been following some of his steps. Then Piotr Kruschel, Robert Beck, Bernd Schmidt, also some particular, so closely tied also with ideas of Helmut Friedrich. And then there are the people who have worked, say, more on the problem of the nonlinear stability, say, of the Minkowski spacetime, and now so the Kerr spacetime or other black hole spacetimes, for which also the issue of asymptotics is relevant. And then more recently, there is work from the school of microlocal analysis of Melrose, in particular Peter Hinz and Bashi, who are also made important contributions to this. And I should also mention some Leonard Kerberg, so also young researcher who has also been studying the role of spatial infinity very recently. Okay, so I just say that so there's some people who have worked on this, but this is by no means comprehensive. Okay, so in the talk about asymptotics, I definitely have to mention this definition by Roger Penrose, just mostly because of its say historical and influence in the field of the notion of asymptotic simplicity, right? Which is, well, so there is some literature, so almost basically 60 years, as I will mention. And then the idea here is that you want to describe or characterize as a universal structure that allows you to describe isolated systems in general relativity, right? And then Roger Penrose puts this definition forward, and the idea is basically a particularly simple spacetime is spacetime where you can compactify in a way similar to that of the Minkowski spacetime. And this is at null infinity, right? So this definition, crucially, doesn't say anything about somehow how the two components of null infinity connect to each other, nor it says what happens, say, at the endpoints of null infinity, right? So to say, go to the future and to the past, right? And a central aspect of this definition is the requirement that this compactification to be smooth. And well, so this is now the starting point of my discussion. So why this needs to be the case. Okay. Right. Okay. So just to stress, so what is the idea behind this? So somehow the motto is that to provide a geometric framework to study the asymptotics of gravitational field, right? So all or most of the work prior to say Roger Penrose's idea was somehow based on the use of asymptotic expansions, right? And Penrose's idea is then, well, if you have this boundary, then you can do, say, more rigorous geometric differential geometric calculations at the conformal boundary, and then you can have somehow forget about these nasty asymptotic expansions. Okay, so this is the idea. And just as a side remark, so well, as I said, so it turns out, so 2 weeks ago I was organizing this meeting in Royal Society in London, so with asymptotics of conformal methods in general relativity, so similar topic of today's talk. And then Roger Penrose was giving a talk there, and then basically it turns out that although it was not really planned like this, so it happened to be like the 60th birthday of Scry, right? Yeah, so it's an old field, right? But what is, I think, remarkable is there are plenty of things to do still here. Okay, so just to stress the points of about the smoothness of Scry, so the idea of Penrose is the following, right? That you can encode the decay of fields in the asymptotic region, say radiation, through the degree of smoothness at null infinity, right? So this is somehow the general overview, and then there is somehow a corollary which is less often cited, but I think this is important for this talk, is that if you don't have full smoothness, so then you only have a certain number of derivatives of your field, say the Weil curvature, for example, then you have restricted smoothness. So you have this restricted smoothness, then you have a modified decay, right? So this means that the smoothness actually tells you that your field will decay in a different way, right? So precisely a way which is different from what is known as the peeling behavior. Okay. So as I mentioned, this word peeling. So I just want also to be on common ground. So what I mean by peeling here, by peeling, I mean a certain hierarchy for the decay of the various components of the Weyl tensor. So you have the Weyl tensor can be, so the components which can be encoded in 5 complex scalars, which are the components with respect to a particular frame which is adapted to the structure of null infinity. I will say a bit more about this later on, but the point is that you have this adapted frame and you assume that the spacetime is asymptotically simple, in particular meaning that, say, the Weyl tensor is smooth at the conformal boundary, then you have this decay, right? So you have the slowest decaying component, psi4, which is the radiation field, and then at every component you gain an order of decay, with the fastest decaying one is this psi naught, right? And then this R is a certain parameter along the generators of some adapted null cones. Right? So this is an idea of 65, 63, thereabouts. Okay? So, yeah, so this is somehow, this definition, I mentioned this, right, because it has been very influential in the literature, right, and really has spanned all the sort of work I've been studying, say, in the last 10, 15 years. Okay, so given, I mean, this is the definition, so then there are some natural questions, right, so regarding asymptotically simple spacetimes, right? So the first one is how large is the class of spacetimes with a smooth Penrose compactification, right? And then one way of trying to address this in a systematic manner is to pose a suitable initial value problem, so that you give you some initial hypersurface, a Cauchy surface, where you prescribe 3-metric intrinsic curvature, and then you want to prescribe these quantities, so these objects, in such a way that the resulting spacetime will be asymptotically simple. Right? So how you do that? Right? So in particular, you get the smooth compactification. Right? And then if you find a way of doing that, then you can ask the following. So is the class generic or not, right? To say that it consists of points, so to speak, on the space of data, isolated points, or it's just like an open set, right? And then, of course, that's what you would like to have, right? Or you would like to have something that is open, right? So, and then it's clear all throughout that to do this, right? So then to construct this spacetime, so this class of spacetimes, then you need to have some extra condition, right? At least it's plausible, right? So not any arbitrary piece of data or a choice of data will very likely not give you spacetime, which is asymptotically simple. Okay. Okay. So why is this? So why it is that one needs to put some extra conditions? Well, so the point is, and this is really at the core of what is known as the problem of spatial infinity, is an observation by Roger Penrose, which is the following. So when you do this Penrose compactification of the Minkowski spacetime, you can get this compact manifold which is completely smooth at every of its parts. But then as soon as you put some mass of this in the spacetime, right? So then this mass will produce a singularity of the conformal structure at I0, so the point of spatial infinity. Right? So to say, so you have your conformal boundary scri plus scri minus, and then they meet at these points I0, and then the statement is that the conformal structure of the spacetime, right, given by the particular metric that is solving the Einstein field equations, will have a singularity in the Weyl curvature, right, which somehow seemingly spreads out, right, towards the future, not entering into the spacetime, right, but nevertheless the consequences of the singularity somehow one would expect them to spread out along null infinity, just basically because null infinity consists of is a null surface, or two null surfaces, and then contains characteristics. So any singular behavior is likely to spread out, right? And if it doesn't, then it would be interesting to understand what are the structures that somehow contain this singular behavior, right? So I just want to stress the following, that in following Penrose idea, right, spatial infinity is naturally seen as a point, right? And then somehow, if you are in a neighborhood of spatial infinity, so you get this counterintuitive picture that I have in here, where the actual space-time, right, is the region outside the light cone, right? So this is the space-time, right? And then somehow the singularity of the conformal structure seems to be propagating inside the light cone, and somehow in a way is causally disconnected what happens inside the space-time, right? But nevertheless, it may still influence what happens at the light cone. Okay. And so, as I said, so this was known already in the mid-60s, right? And that's why when people try to study systematically how to construct asymptotically simple spacetimes through Cauchy problems, they formulated problems which avoid spatial infinity. And how can you do that? Well, you can do this by having initial value problems where you prescribe data on an hyperboloid. So what is an hyperboloid? It's a space like a hypersurface, which instead of ending at spatial infinity, it actually finishes at null infinity. And so I put here an example of this hyperboloid, right? And so the point, which is somehow not really appreciated, cannot be captured in this picture, is that this surface, well, so to reach null infinity, becomes asymptotically null, right? So the point is that this Penrose diagram representing somehow the resulting space-time has a huge level of distortion, right? So then you don't see that here, right? So then Helmut Friedrich, in the first nonlinear stability result for the Einstein field equations in the literature in '86, what he did is he prescribed some initial data on this hyperboloid, which is data which is close to data for a Minkowski spacetime, so it's a perturbation of Minkowski spacetime, and then he actually can prove that you can recover the whole of the future domain of dependence of this hyperboloid, right? And then in particular, the spacetime that you obtain from this has a nice piece of null infinity, right? So this is called semi-global rather than a global statement because as you are prescribing data on this hyperboloid, then you cannot recover the whole of the spacetime, right? So in particular, if you wanted to recover everything that is at the past, say, so you cannot recover this triangle here, right? So you cannot, so you need somehow to have something that is global, you need somehow to include the discussion of this point, right? But nevertheless, it was, so I think that the value of the result is really that identified that there is a difficulty and finding a way, well, to nevertheless gain some insights despite these difficulties. Okay, so I guess then that the next piece of information or piece in the puzzle comes from the work by Christodoulou and Kleinerman in the 90s about the global nonlinear stability of the Minkowski spacetime. Right? So then they really what they put forward is they want to prescribe really data on a full Cauchy hypersurface. And then what they do is that, well, if this data is small, so it's to say it is close to data for the Minkowski spacetime in some particular specific sense, while measured in terms of functional spaces, then they can show that the resulting spacetime exists globally to the future, is geodesically complete, right? And then they can also estimate the decay of the gravitational field at null infinity, right? But what they observe is that they cannot recover the peeling theorem, right? So the decay of the gravitational field that they observed is more general. Right? So then, at the time, so there was a lot of discussion in the field of whether this is a technical problem, so because maybe their estimates were not good enough, and then if you were more careful in the estimates and you looked at things in more detail, then you may be able to get really the precise decay. Or, well, the other possibility was, of course, say that there is something more fundamental happening here. So now, what I want to say is that, well, after 30 plus years, I think the general consensus is that there is something, well, is something more fundamental here, right? It's not really a technical glitch of their approach, right? So. Okay, so now, right, so as I said, so basically the previous result somehow hints at that generically you will not be able to recover asymptotic simple spacetimes. But so there is a nice trick due to Piotr Kruschel and Erwan Delay, which builds on other techniques by Corbin and Juan, right? So this is our geometric analysis. We have studied ways of constructing solutions to the constraint equations of general relativity with prescribed asymptotics. So in particular, what they have shown is that you give me some asymptotically Euclidean initial data for the Einstein equations, a vacuum. Then it's always possible to rearrange this data such that you, in the exterior region, for the asymptotic region, you have, say, exactly data for the Schwarzschild spacetime. Then you will have a transition region, and then you will have inside in a compact set, you will have your part of your original seed initial data, right? So this is your arbitrary data that you are prescribing. Then there is a transition region that I put here in green, and then there is this asymptotic region, which is the asymptotic region of the Schwarzschild spacetime, right? So this asymptotic region of Schwarzschild spacetime is well understood, right? And in particular, we know that for spacetimes which are time independent, so null infinity is nice, so it's smooth, right? So then basically you guarantee that in this region in red everything is under control. But then, so the way you construct your global spacetime is that so you assume that this region in blue is a perturbation of Minkowski spacetime, and then from that, then you can draw this line in blue, which is again is an hyperboloid. So it's again a surface, hypersurface, which becomes asymptotic in null and reaches the scribe plus. Okay, and then if you somehow your data is small, then this will imply data on the hyperboloid which is small, and then from once you reach the hyperboloid, then you can fall back on Friedrich's result of global nonlinear stability, and then you can recover whole space-time. And then the point here is because you avoided all the difficulties of a null infinity, so you can actually guarantee that the whole space-time is asymptotically simple, right? The conformal boundary is smooth. Right? So it's a very nice construction, but then of course the critique is that, well, so it looks very artificial, right? So one would like to know, although this gives you your desired space-time, one would like to know in more detail whether this is the only way you can construct this type of space-times or there's something else that can be done. Okay, so in this direction, following the steps of Helmut Friedrich, so he sets himself to construct what he called the regular asymptotic initial value problem of spatial infinity. So this is in a snapshot a detailed structure of spatial infinity from the point of view of an initial value problem. And the idea is, so I to try to explain what the words mean. So asymptotic means that the initial value problem allows you to reach up to spatial infinity. And regular means here, in this context, that despite the fact that you know that there is a problem with the conformal structure, which is singular, somehow you can construct, nevertheless, equations which don't see that, and you also can construct data which also somehow also don't see that, right? So for which these singular equations this singular behavior is not regular, right? And then if you understand the claim is that you understand this initial value problem, then somehow you could study the genericity of the assumption that leads to a smooth null infinity, right? And so then, but the key observation is that if you stick to the original picture by Friedrich of having spatial infinity as a point, this will be difficult, right? So you have to somehow deform, or you have to do something here, right? So you have to change this picture, right? And then this comes to this representation of the cylinder spatial infinity. So a picture that I will come back again many times during this talk, right? But then there's like a first encounter. So the idea is first that you have this point, a spatial infinity, and you don't want a point, right? Because it's very restrictive. So how you get rid of a point? So you blow it up to a sphere, which is somehow what you are doing here. So this is your initial hypersurface. And then it turns out that, so one can change the conformal gauge, so somehow they choose the conformal factor that complexifies your space-time, so that instead of having something that has no dimension on the time direction, so it actually has a finite time extent, right? And then, so this becomes this cylinder, a spatial infinity, so it's a surface, a structure that relates the data on initial hypersurface with somehow what's happening at future and past null infinity, right? So in this picture, turns out, as you see in following Penrose's conventions for drawing Penrose diagrams, you would put the null infinity as a 45 degrees line, right? So this picture here is a coordinate diagram. This is not a conformal picture, right? So it's actually quite important. It's not a conformal diagram. Right, so that's why null infinity by being null looks like these horizontal hypersurfaces. And then the idea is that, so this construction has some sort of conformal invariance, so it makes use of certain conformal invariance called conformal geodesics, so certain type of lines of curves to generate the coordinates in this setting, right? And in particular, it turns out that this cylinder, so the generator cylinder are also these conformal geodesics as well, right? So the idea is then that somehow this cylinder allows you to connect what is happening in your initial hypersurface, at the end of your initial hypersurface, with what happens at the intersection of null infinity and spatial infinity, right? Which are these sets I plus and I minus, which in the following we call them the critical sets, right? Sometimes people call this is the end of scry or the beginning of scry, right? Depending on which direction you are coming. Just to say that this picture, it's coming from the 98, but there were some ideas like this in the literature. So in particular, there is Ashtekhar's framework, so which involves these hyperboloids at spatial infinity. So this is actually very closely related to each other. So remarkably, the connection was not really worked out for a while, but yes, so it turns out that if you are in this picture, then you can somehow change to Ashtekhar's representation of spatial infinity with these hyperboloids. These hyperboloids of spatial infinity. And of course, I guess the motivations between these two frameworks somehow are different. Right? Ashtekar was interested more in study of conserved quantities, for example, right? And here, I think the focus of this is more on formulating a Cauchy problem. Okay, so as I said, so there are a lot of details that I'm skimming, but I just wanted to do this very conceptual. So why this structure, this representation is very important, and this is holds for the cylinder, a spatial infinity, but also say Ashtekhar's hyperboloid, is that this cylinder is a total characteristic of the Einstein field equations, or the conformal field equations. So this means that when you evaluate the conformal field equations, which are a conformal representation of Einstein's equations, when you evaluate them on this cylinder, so all the equations become interior equations. This is to say that you lose somehow the derivative in the radial direction disappears from your system of evolution equations, and then so you get an interior system of equations where if you have data at some intersection, you can evolve this data towards the future and then towards the past. Right? So this is actually quite satisfactory because if you look at this picture and then you say, well, you're including a boundary here, then you could complain, well, so what you are doing here is you're introducing a boundary value problem for the Einstein field equation, right? Where you have to describe some boundary data. But in fact, the fact that this cylinder is a total characteristic precisely doesn't allow you to do that, right? So there is no freedom of putting boundary data here, right? As soon as you know, so the value of your fields, say at the end of your initial Cauchy hypersurface, all the data is determined on this boundary, right? So you don't have to worry about boundary conditions here. So, and then in particular, we also tell you that if you have some data here, in particular, you can know the value of the fields at these critical points, for both to the future and the past. And then, so in a more technical language, it allows you to compute some solution jets. This means that you can compute higher derivatives of your fields as well, right? So in principle, so you can basically use the solution jets to compute some special type of asymptotic expansions, right? That connect the behavior, the initial hypersurface to the conformal boundary. Right? So I think this is somehow in the snapshot somehow why this construction is so important, right? So now, if you somehow follow this program, right, or these ideas, then and you start to integrate the Einstein field equations using this approach, right, to constructing these solution jets, then so it turns out that well you can compute these coefficients, right, on these expansions. In principle, so you give me some particular data, modulo some computational complexities, so this can be computed. So in practice, you would do this with a computer algebra system. So you have a big program that takes care of this, and then if you do that, then you start seeing that your solutions are very particular pieces of the jets generate logarithmic divergences at these critical sets. And then, as I said, so these logarithmic divergences somehow are an indication that null infinity will not be smooth, right, in the sense of Penrose. But then, so there is a lot of structure here, and this in particular allows you to realize that you can actually fine-tune the data to eliminate certain singularities in the future, right? So then you don't like that particular term with that singularity, then there is somewhere in the data where you can fine-tune things or set something to 0 that will preclude the appearance of this singular behavior. And so just to be to be a bit more precise, what I mean by this, so I'm presenting here so like a summary from paper in where this program has been carried out by on the particular case of time-symmetric data. So you know time-symmetric data are data where you set the extrinsic curvature equal to 0. So all the freedom on the free data that you can specify is a conformal class of your initial metric, right? And then precisely the properties of this the particular conformal class will determine how the behavior of your solution, right? So this what I put here, this assumption, just put it here in case someone wanted to look at the particular details. But basically, what you are assuming is that you have asymptotic Euclidean data, and then so you can choose your gauge so that basically the trimetric close to spatial infinity is the flat metric plus corrections that go to order cubic. And then if you do this, now you can do this integration, right? And then you can find that the gravitational field, right, or the Weyl tensor will satisfy this behavior, right? So you still have the psi 4 going to 1 over r, right? So the radiation field, and then, but then for psi 2, the Coulomb field and higher, then you have this very, very slow decay, right? So he's definitely breaking, not following peeling, right? I have
a question.
Yes.
12. Does that include Schwarzschild?
This includes Schwarzschild as well. This also includes Schwarzschild.
You should
but
it's X cubed.
X cubed, right? And this is somehow the conformal metric, right? So the mass is outside, right? It's somehow hidden in the conformal factor. Yes.
That fall off from psi 2 means that the mass is not well defined, or the bonding momentum not well defined?
No, so the bonding momentum actually you can check that. I think the bonding momentum is well defined. I think this is a paper by Piotr on this.
Is it just the imaginary part that's blowing up?
No, so you also have real part, but it turns out that the extra factors they can be integrated out. So
I see. So they have 0 L equals.
Yeah, so they're like a divergence term, which you can remove by integration by parts. So it's actually quite remarkable, right? So it's not obvious, but yes, so it happens to be well defined.
Does that follow from the Bianchi identity?
Yes, that would come from the Bianchi identities, yes.
That's right. So that
Yeah.
parts of Roger's argument can fall off the low ones as well.
Yes, yes. No, that's right. And then, so I just to stress the point, right? So you can go more, right? So for example, you require that, so this Bij is the so-called cotton tensor. So cotton tensor is, as you know, so is the analog, three-dimensional analog of the Weil tensor. So it characterizes conformal flatness. So it's a qubit, so it's a derivative of the curvature. And right, so precisely if the cotton tensor of a metric vanishes, then this metric is conformally flat, right? In the same way as the Weil tensor is. And turns out that this cotton tensor appears somehow in the discussion of smoothness null infinity. And then, particularly, if you require that the cotton tensor vanishes not everywhere, but just precisely at spatial infinity, right? So just at the last point of the data, then you recover one order more in expansion, and then putting more requiring more derivatives, then you can push the logs further away, and then finally by putting three conditions, right, on cotton, the symmetric and trace-free derivative, and then the second symmetric trace-free derivative, right? So you see these are conditions really at infinity. Right? So it's not a condition everywhere on the slide, but it's just really a purely asymptotic condition. Right? And then in particular, it turns out, as a side remark, that in fact, these conditions are closely tied to the characterization of static and stationary solutions in general relativity. Right? So static data satisfies somehow the string of these sort of conditions, right? So at spatial infinity, somehow, which somehow indicates that stationary solutions have a nice behavior at spatial infinity, as somehow you would expect. Okay, so which is precisely so what I wanted to say in this slide, right? So in general, so you know, so stationary spacetimes, so one can prove, right, that at least in the setup are as regular at near spatial infinity as one would expect, right? So that's like the prototypical case where you have asymptotic flatness, simplicity, right? So, and you will not see these logarithmic conditions. But then, of course, so just to say that, I mean, it's not direct, right? So there is some heavy calculations involved in this, but then somehow the natural question after you somehow realize this is whether there is any type of rigidity implied smoothness at spatial infinity. Well, is it that every time that I require things to be, say, completely smooth, I will get a time-independent space-time, for example? Could be a natural consequence of this, right? That would be very, very bad, right? Well, I mean, it's an interesting question.
So, but you assume that some point that the extrinsic curvature was zero?
Everywhere, right? The stationary is more general, right? So
some decay for the extrinsic curvature?
Yeah, so the question would be really to check whether, so certainly for static spacetimes, it seems to be the case, right? But if you have extrinsic curvature, then probably not, right? But you would like to see somehow what is the interplay, right? Of particular of the K, of the extrinsic curvature. So something that I should have probably mentioned, I haven't said before, is well, so if you have spacetimes admitting these expansions with logarithmic terms, that like the ones I was showing here for the Weil tensor, are known as polyhomogeneous spacetimes. Somehow that's the technical name. And and then, so although people had evidence from many directions that these log terms will appear, right, and hence somehow destroying the smoothness of null infinity, there was no proof that actually that you have these polyhomogeneous spacetimes, right? And so recently, Hinz and Bashi, Peter Hinz and Andreas Bashi, they have yet another proof of the global nonlinear stability of Minkowski space-time using techniques of macro-local analysis. And then what they find is, so they can prove that, in fact, that generically you will have these polyhomogeneous expansions, right? But so I guess the key point here is that the results are not sharp, right? So the gauge is not ideal. And then, in particular, you get also logs in the expansions in space-time you wouldn't expect to have, like Schwarzschild, right? So in their gauge, so even Schwarzschild gets Lomme logarithms, right? So which is a complaint not about really the method, but I guess the particular gauge they are choosing, right? So if they were able to refine their gauge, so I'm sure that then you will get a sharper result, right? Where even so the time-independent space-time have no logarithms, right? But I think, nevertheless, I think this is a fantastic piece of work and probably shows the way how to close this program, right? Okay, and then just before going to the second part of the talk, well, I guess the natural question is about why we care about all the things that we're discussing, right? So in the way I've been presenting this concern about asymptotic simplicity really arises from a study of nonlinear perturbations of Minkowski space-time. Right? So this was the natural setting where these questions and these techniques were developed. But so I want to stress that, in fact, the conclusions for this analysis are generic, and this really independent from the setup of stability, right? So if you want to, of Minkowski, right? If you want to study stability of Kerr, you will face the same, right? Or so even you have, so you are perturbing strong fields, right? And then so my claim is that, and this is what I want to discuss later in this talk, that this construction by Henus Friedrich really provides a framework to study the asymptotic behavior, say, for example, of charges and other observables and how they relate to initial data. Okay? Right, so this is somehow concludes the first part of the talk, so somehow like a very long introduction, but I hope you have found this interesting, so it gives you somehow a general picture where I'm coming from. So any questions up to here before I move? All right. So now what I want to do is talk to you about BMS charges and spatial infinity. Right, so then, so just brief reminder about BMS charges. Right, as you surely know, so the symmetry group of null infinity is the BMS of the Bondi-Messner-Sachs group. And well, so then this, you have this asymptotic notion of asymptosymmetries, which are described as characterized as solutions to the asymptotic Killing equation. So this gives you some transformations of null infinity of Scri, which preserve the structure. Right? So this is somehow the idea behind. And among these asymptotic symmetries, so one preferred or important class is that of supertranslations, which are, you can regard this as reparameterization of null generators of null infinity. Right? So you have certain parameters of null infinity U. You can then, the supertranslation allows you to add an arbitrary smooth function of the angles, right? So we basically say in an active picture, so you have this particular cut of null infinity described by this value U, and then by applying the supertranslation, do you shift this, right? In an active picture of the transformation. Okay. Now, as I already mentioned when I was talking about the Peeling theorem, so this Peeling statement, right, is done in a particular gauge, right, which is somehow, there's a prescription how to set up this gauge. If you compute things outside this gauge, even if you are in a Peeling spacetime or a smooth, so a totally simple spacetime, you may not be able to see Peeling, right? So you need to really adapt your your gauge, so your coordinates, and your tetrad to the structure of the geometry of null infinity, right? So there is a particular prescription to do this, and in particular, so you require one of the legs of your tetrad. So you are using a tetrad formalism. You want it to be chosen so that it's aligned with the generator of null infinity, and then they will have the other null leg somehow pointing inwards, and then all the various parts of the field are propagated, of the frame are propagating in a particular way, which I'm showing here. So you use the so-called boundary coordinate. So you have this retarder time, this radial coordinate along outgoing light cones, and then some particular choice of angular coordinates on the two sphere. And then, as I said, right, so one of the vectors is chosen to be tangent to scry, and then is parallelly propagated, right, with respect to itself. And then you choose also a normalization for the boundary coordinate, and then was also the other vectors on your frame, which I call E00, so which is the L, right? So it's basically the gradient of the boundary coordinate, right? And then, so even with this prescription, so then in this gauge, so there is some residual conformal freedom, and in the choice of the frame, which can be used to set to zero certain components of the connection, in the case of L symbols, and also because you are working a conformal picture, right? So I'm always thinking about a vacuum space-time, but then when you do a conformal scaling on a conformal picture, so then the space-time has a non-vanishing enriching tensor, right? So which is basically given by the conformal factor that you are using to do this conformal compactification. But then it turns out that so you can also choose your conformal factor such that certain components of the Ricci tensor vanishes. For example, you can always set the Ricci tensor, the Ricci scalar equal to 0, for example, right? So this is one way of doing this, but not the only way of doing this, but there is a convenient way. Okay? So this is somehow, so you mentioned this, right, because it somehow plays a role in my later discussion. Right, so then, so the other ingredient I want to discuss are the so-called spin-2 equations. And so, you know, so the spin-2 equations, if you are on flat space-time, so these are equivalent to the linearized gravity. So this is a way of representing the linearized gravity. And then, so these equations involved are balanced 4 completely symmetric spinor satisfying these equations. And then for these fields, so given a supertranslation, one can always define a so-called BMS charge, right, which is quantity Q, which is basically integrating the Coulomb component of the spin-2 field, right, against a function lambda, which is a smooth function on S2. Right, so in particular, it's, I think, convenient to think about this lambda being a particular choice of spherical harmonic, right? Right, and then basically what you are doing is extracting this harmonic on the Coulomb component, right? And then this gives you a charge on null infinity. However, so for a dynamic spacetime, so with spacetime with radiation, so you can compute the charge here C1 and then in C2, so in 2 different cuts. So the charge is not conserved, right? So it obeys a certain flux law, right? And well, so I'm putting here this at future null infinity, but obviously you can do the same mutatis mutandi. You can do this for past null infinity, right? So then, of course, because you can evaluate this at different cuts, so why not, for example, compute the limit of the charges, say, along future null infinity and push this and compute the limit at spatial infinity, right, from the future, and you can also do from the past, and then you can ask what happens, right? Yeah. So they would like to ask. So, and then, but of course, there are several questions here. First, under which conditions are the limits well defined? Are the charges at the future and the past related in some way? And so there are a lot of people, so Strominger, Marc Henneaux, Prabhu, and so on, who have looked at these various angles. And then with my student Marin Magdi, so we were somehow, because of the obvious connections with the framework of Cylinder Spatial Infinity by Frederick, we decided, well, so that would be interesting to also look at this from this perspective, right? And then, so our idea is really to look at this matching problem using an initial value problem, right? So using this representation of spatial infinities, and then the advantage here is that to do this calculation, right, this identification, you have to make some assumptions, right? And then the nice point here is that you can do this in terms of assumptions initial data, right? And then so a strategy was really to try to compute these limits, see when they actually do exist, and then if in the case where it exists, then we can write the charges in terms of free data. Okay. And again, so just to remind you about this construct, right? Because somehow this is not somehow very well known, right? So this is somehow the standard picture that one would have for spatial infinity, right? A la Penrose, and then what we are looking at, is at the space-time in this region in gray, right? And then here I just put in red some outgoing light cone and an incoming light cone, right? And in this picture by Frederick, so then this is distorted, right? Because it's not a Penrose diagram, so then these null geodesics have this form, and then you have these curves, conformal geodesics, where are used to construct the gauge, connecting future and past null infinity, right? And the initial hypersurface is this one here, right? So this is somehow the generic framework. And then again, so one can, so this framework allows you to compute expansions of the solutions to this spin-2 equation, right? But then the point is that this is given a different gauge, right? Which with different coordinates and a different choice of gauge, and then the location of the conformal boundary is also somehow given by some coordinate condition. So you have to relate this, called it Friedrich gauge, with the Newman-Penrose gauge. And well, so you can do that, right? It's not very exciting with a calculation, so you can find somehow the Lorentz transformations that move from one gauge to the other, and then there's also, in principle, a conformal factor involved that adjusts the gauge. So here it turns out that this is trivial. So you can do this, and you can obtain for Minkowski spacetime, you can obtain the explicit expressions for this. And well, so the point is that we are looking to compute these charges, we need to compute or find an expansion of this Coulomb component of the spin-2 field, right, in a sort of a Taylor expansion respect to rho, which is somehow radial direction, away from the cylinder. And then there are some coefficients here associated to every multipole spherical harmonic, right? And these are functions that depend on principle on time, right? So this is a very general class of data. So we are allowing a leading order an arbitrary number of harmonics. So usually, say in the literature of initial value problem in relativity, usually one has somehow a constant in front of the y00 harmonic, so the 1, right? So here, so this is very generic and it's boosted, right? So you need this so to be able to have non-trivial charges. And it turns out, so as I remarked, so then actually one can prove that this is sort of solutions to spin-2 equations exist, right? So it's not only really an assumption, right? But then so we have like a theorem that tells you that yes, so you can always consider fields of this form. Okay. And that now, so that really the question, as I said, is that one has to determine these coefficients appear in the expansions, which are functions of t, and then they satisfy a very nice ordinary differential equation on this cylinder. So this is precisely the point about the transport equation, right? So if you know the value of this field A as some cut of the cylinder, then once you solve this equation, then well, so you know basically everything, right? And it turns out the general solution to this equation is, well, it's a Legendre equation, right? And then it has a solution which is regular, it's a polynomial, and then it has another part which is singular, which is a Legendre function of the second kind, which always contains a logarithmic term, right? So this tells you that generically solutions to the spin 2 equations will have logarithmic singularity, so they will generically not be smooth at null infinity, and this is somehow a problem for computing BMS charges, right? Because precisely this is the quantity you need to compute, right? So this has to be finite, the critical set. So this precisely tells what precisely having solution in this way allows you to fine-tune your data so that the charges are well defined. Right? So you obtain this proposition here, which is in terms of right, so pieces of data. So depending on whether the L defining your spherical harmonic is odd or even, you have a condition on the field or on the coefficient or its derivative initially, right? And then, well, so the nice thing is that this data, so the point is that the spin 2 equations, they have constraints, right? So these are Gauss constraint. And so you don't know whether these conditions can be set in terms of free data. But in fact, it turns out this is the case. So one can prove that, so there is a certain third-order operator, somehow this was found by Lars Andersson, Bagdal, and Judio, who basically you give me any spin 2 field, you apply this third-order operator, and then this generates you a spinor, rank valence 4, which satisfies the Gauss constraint. So basically, this operator is a machine that computes TT tensors, basically on flat space, right? So somehow the takeaway is that the actually conditions are actually conditions on data that you can freely specify. Okay, so it's nice. And then,
if you think there's an initial value problem, though, can you guarantee? I mean, you imagine yourself specifying the initial value arbitrarily, and then you're forced to have log terms generically.
Yes, so this is basically a statement, right, for this spin 2.
So somehow aren't you at risk of being, so to speak, teleological? I mean, sort of specifying your initial data by what it might do in the future.
Well,
is there some logic as to why it should always be like this? Why it should not have those log terms? I mean, I can see if you don't want them.
Well, I mean, so I guess if you don't want to be teleological, so this means that generically the charges will not be defined, right? So this is if you want to live dangerously, then of course, then the generic space-time will not have well-defined charges, right? And then this, I guess, the way out, right? But then
well,
you.
You could argue maybe if it doesn't have well-defined charges, then it's not physical. Is that
There is another difficulty if you don't impose such conditions, which is that the action diverges. And the kinetic,
okay.
This type of parity conditions are necessary to have a symplectic structure which is well defined.
Okay, I see. Okay, so these are more fundamental.
Well, I don't know, but it goes in the same direction.
Mm-hmm. Yeah. Well, in any case, somehow the outcome of this is that yes, so you can compute the charges, and you actually find that the two charges so you can be identified basically. Right, and in fact, I made a mistake here. I should have put 0 here. So not 1 and -1. So it should be 0 and 0 here. Well, so basically the charges can be identified, right? And then this doesn't assume any, say, antipolar identification, say, a la Strominger, but I agree, right? That this then so you're fine-tuning your data, right? So this is somehow the takeaway.
But I mean, I guess these terms will automatically be 0 if it looks like plus 1 over r. Well, it depends on like curve plus 1 over r squared, then this would be satisfied.
Yes, that's right. And I will talk briefly about the GR case, and I think I will come back to this point.
And that's and would that agree with that? That would probably agree with Leonard Kerberger's kind of criteria as well, would it?
Yes, I think so.
So maybe you're just looking at freakishly sort of slow Formal conditions.
Mm-hmm.
To get the log terms.
And well, so I guess so that just to round up this part of discussion, right, is that, well, in fact, so you can somehow then prove somehow the antipodal matching, right? But we are resorting to this, well, you can prove the identification of the charges without having to use the antipodal matching. But then, in fact, so I guess another way of saying this is that the antipodal matching is some sort of in disguise, is a regularity condition somehow, right? So this is another way of reading this, right? By requiring this antipodal matching, you make an assumption implicitly about the regularity of your solutions, right? And then just to round up here, so I've been talking very long, so I just want to talk about the case in GR, and it will be quicker, right? Because the details are somehow similar in a sense, and this is work in progress, but I think it's very interesting and very promising, right? So these charges in this case, also you have in GR, there is a correction to these charges. If in addition to the Coulomb field, so you have this term here, it has to do with the news function, right? So it has some information of the radiation on the, say, in your space-time, right? And yeah, so then to compute the charges, you have to be able to say something not only about the Coulomb field, but also about this extra piece here, so that makes calculations a bit more involved, right? And then again, because we are working on initial data, so we have to choose. So one of the main questions in this program was to choose a class of data which is large enough so that when we compute the charges, they are non-zero. And then, fortunately, there was some work already in the literature that would actually tell you that there is a class that is relevant for us. So if you have the trimetric, which has the standard like Schwarzschild-like behavior, but then there are these extra terms at the same order with a function alpha here, which is a function of the angles, which are basically like a boost term, right? So I indicated here, and then all these quantities here, the A, the alpha, and then for the Kinsey curvature, there is also a smooth function B, and then a constant vector, so function beta and a vector B, which can also be freely specified. And then, so this is a non-standard trivial statement, right, which makes use of gluing techniques as well, like in the crucial delay spacetime, where you prescribe this asymptotic, and then you can glue this behavior to some interior data, right? But you have prescribed the asymptotics in the way you want, right? And it turns out, because advertising what is the outcome, is that precisely these functions here were the ones that enter in the computation of the BMS charges. Right, so somehow, so to answer Lionel's question, then in fact, right, if you if you have like something that is like very close to care, so you put, well, I mean, so care would also have a boosted slice, but if you want to have a slice of care which is not boosted, then you don't have these terms, right, or Schwarzschild. And then again, so the idea is somehow similar, as I said, so just more complicated. So you have to use the cylinder to compute the charges as well. So I guess the only caveat is that we are really in formal territory, but well, just forget about it for a second, in the sense that we don't have really a theorem, like contrary to the spin-2 case, where it tells you that really you have, in fact, you do have solutions with that asymptotics, right? So this is something that we assume, but we're happy to do that for the time being. And again, somehow, the main somehow outcome of this calculation is that for this class of data that provides you non-trivial charges, the behavior is like in the linearized gravity. Right? So in particular, again, so you can compute the Kroon field, and again, you have this split in terms of the Legendre polynomials and the Qs, which are logarithmic singularities. And then the key point is that the extra ingredient on these charges was the function sigma to this new tensor, and this actually, for this class of data that I put here, actually goes to 0 towards the end of future null and past null infinity. Right? And now the takeaway is again that there is some regularity conditions that can be controlled by putting conditions on the multipolar structure of this alpha and beta.
Sorry, you're using sigma for the news, not the share.
For the share, I meant, yes.
So but having it go to 0 at I plus is a sort of gauge condition, or one to gauge. Maybe is that what you meant?
Well, but not only, right? So there are extra.
Well, I guess if there was some time dependence, then you couldn't set it to 0.
Well, so you can, but there are other parts of the curvature of the connection coming out. So when you transform into the Friedrich gauge where you do the calculations, you get all parts of the connection, and then all these things also go to 0.
Right.
Yes, so that would be the statement. And well, I guess somehow the takeaway of this, which is somehow maybe surprising, maybe not, is that again, so these charges can be identified in terms of particular pieces of free data for the Cauchy data, and you can identify the charges, right, and past and the future, and then you don't have to make again use of the antipodal maps, but only the requirement that these charges are well defined. Okay, so this is somehow the case. So yes, so I wanted to show this example, so somehow they show that indeed this framework, right, is useful to do sort of calculations, and then there are other things that you could make think of, like what is the behavior of the bonding mass towards spatial infinity, right, under which condition is true that the bonding mass and the ADM mass agree on the limit, and well, many other things. I'd say also memory effects, for example, which could be computed in terms of also conditions on terms of initial data, for example.
Sorry, which charges were you including there? You're choosing the super translation
charge? Oh, we only did the super translation charges, yes.
I see, but not angular momentum or...
No, we haven't done that, yeah. Okay, so just to conclude, so then there are some takeaway messages. So it has been a long talk, so talking more than an hour now. But just to, well, I guess this is the selling point, so that this representation is very useful and can allow you to understand the assumption behind the asymptotics, or the standard formal theory of asymptotics. And then I guess the other point that I've been stressing a lot here is that these assumptions are non-generic. But then, maybe Lionel regards this as teleological, but I'm happy to live with assumptions on free Cauchy data, right? So on the free parts of the data. And but just to stress that this is definitely not completed, right? So there is a lot of things to be done. And in particular, so I mentioned that the expansions for GR are still at the level of formal ones. So then one would like to still to have a rigorous statement that tells you that, yes, there are actually solutions to the Einstein equations, which this particular type of asymptotics, right? And this is something, if one had this, then one will really have a machinery really to determine really the precise asymptotics of the gravitational field at null infinity in terms of specific properties of the initial data, right? So, and then somehow, I guess my claim was if one were to do that, right, and then somehow this problem of spatial infinity will be solved, right? So then we can turn the page, right, and have this thing completely done. And well, just some advertisement if you like this thing. So there is a nice book here by myself where I talk about some of these things, not really the new development, but I talk a lot about the conformal field equations, for example, and this worked out nicely in spinors and so on, right? So, and well, finally, thank you very much for your attention, and it was a pleasure.